an extension of the idea of circuits are going to be two specific types of circuit, which is called an Euler circuit. An Euler circuit is going to be a specific type of circuit to where we're going to use all of the vertices and every edge in G, right? And so we're going to use every vertex and we're going to use every edge exactly one time, all right? So because remember, a circuit, we go through and it's going to basically be a closed walk of that sort of type where we begin and end on the same, or the same vertex, excuse me. Now, Euler's theorem suggests that we can determine whether there's going to be an Euler circuit or not that exists in a certain graph, okay? So for us, if we have a graph that has two vertices of odd degree, or more than two vertices of odd degree, then it doesn't have an Euler circuit, okay, or an Euler path. If the graph is connected and has 0 or 2 odd degree vertices, then it has one Euler path, at least one. And then if a graph contains 0 vertices of odd degree, then at least one Euler circuit exists. All right, so let's take a look at two different graphs and determine if there is an Euler circuit for those graphs. So we're going to take a look first of all, and I'm just going to call this one G because we can. And let's start on, let's say E right here. All right, now the goal is with an Euler circuit to use every edge and every vertex, all right, exactly once. All right, so let's just trace out a path. All right, so we start on E, and then we go to 1, and then we go to A. All right, so we end here, so we're done with that one. And then we're going to take 7, and then we go to B, and then to 8, and then to D. All right, so we're done with that. And then we go to 6. Okay, and again, it contains every vertex at least once, but each edge exactly once. Okay, so we can't go back over the edges. All right, but we can reuse vertices. All right, so and then we can go 5 to A. All right, and that's okay. And then we're going to use 2, and then go to C, and then 5, and then to D, and then to 9 and to F, and then 4, and it looks like we're good with this, to C, to 3, and then back to E. All right, so that's one Euler circuit. Okay, not saying that there are more than one, but there probably is more than one Euler circuit depending upon which vertex you start on. Okay, so that's cool that we were able to find an Euler circuit. But for this second graph, there is not going to be an Euler circuit for this one. And the reason being is because we look and we take a look at the degree of this graph, and it's 3. We take a look of that vertex, excuse me, and then we take a look at the degree of this vertex, and that's going to be 3. And then up here, we have a degree of 3. So right away, we could stop, because remember, if it has more than 2 vertices of odd degree, there's no Euler path. But right here, that has a degree of 5. All right, so if this is like for, let's call this graph H, we can say that H has no Euler circuit since it has 4 vertices of odd degree. All right. So it might be worthwhile determining if an Euler circuit even exists to start. All right. And so if we look at this very first graph that we looked at, which we defined as G, we could go through and we could say, okay, well, B has degree 2 and B has degree 1, 2, 3, 4, 5. All right. This has degree 2. This has 1, 2, 3, 4. All right. This has degree 2. This has degree 1, 2, 3, 4. All right. So, and so that probably suggests to us that there is going to be at least one Euler path. Okay. So because it didn't violate that first law. Okay. Now remember, it didn't say anything about having any vertices of like having one vertice of odd degree. All right, so we should be good with this. All right, as we go through. This actually has degree 4. I think I counted wrong. 1, 2, 3, 4. All right, so that was perfect because it has 0 vertices of odd degree. All right. Now we have another type of circuit called a Hamiltonian circuit. All right, and it's a simple circuit. And remember, simple circuit begins and ends on the same vertex, and it doesn't repeat vertices, but it includes every vertex in G. All right. So each vertex appears exactly once except for the initial and the initial one, which would be the final one. All right. We don't have to include every edge in a Hamiltonian circuit. All right. So for instance, let's call this G if we defined it, and let's start on A. We could go from A to 1 to D to 13 to F to H. All right. And I'll just cross off these vertices as we go along. And I should include 11 in there. So F, 11, H, 12, G, and then 9 to C. Right, so we killed that, we killed that, we killed C. From 4 to E. And we got rid of E. And then we can go to, actually that was 6. So this is going to be 6 to E, and then 4 to B, and then back to A. All right, I'm going to call this 13 or 14, I guess, because it wasn't labeled. 14 to A. All right, so that would be one of our Hamiltonian circuits, okay, for this graph G. Let's call this H. All right, and graph H, we could start at vertex 1. So we go 1 to A to 3, and then to H to 5. All right, and again, I'm just going to cross off the vertices as I get rid of them. And then we can go to K to 7, and then to 8, and then M to 6. All right. And then we still need to get this vertex 4 in there. All right, so we can do this. We can go to 6 to E to 2, all right, and then D to 4. And then we can go back from C to 1. All right, and so what that does is that gives us vertex 1, we have 2, we have 3, we have 4, we have 5, we have 6, we have 7, and we have 8. All right, so it's given us all 8 of the vertices inside of this graph H. All right, so these are going to be our 2 Hamiltonian circuits for this graph, or for these 2 graphs. Okay, so next thing we're going to do is we're going to take a look at isomorphisms, and then the last thing we're going to do in this section is take a look at trees.